Swayam Prabha. Digital India. Educated India.
Welcome to the fifth lecture of the course Marine Propulsion. Today we will be continuing with propeller theory. So, the key concepts discussed in today's class will be thrust loading coefficient from the context of propeller momentum theory, and we will also do some problems based on momentum theory. So, let us continue with the equations that we have derived for axial momentum theory of propellers. Okay. So, I am just showing the domain here. We had the inlet velocity, because instead of the propeller moving ahead with a velocity v, we had defined the actuator disc facing a velocity v at the inlet, and the disc is fixed at a particular position. So, this was far ahead and far behind. The pressure is same in these two conditions, and we have the axial induced velocity ua, which adds up to the inlet velocity, and at the propeller plane. So, the propeller is simulated with an actuator disc which imparts axial momentum to the flow. Here the velocity is Vp at the propeller plane, and there is a pressure jump from P1 to P2 across the propeller disc. So, the key equations that we have derived in the last class were Vp was equal to V plus Ua by 2, where Ua is the total axial induced velocity. Next, thrust is given by rho into area of the disc into the velocity at the disc into Ua, right, where area is the disc area pi d square by 4, where d is the diameter of the disc, diameter of momentum disc, right. Now, next what we will do is, we have also derived the ideal efficiency of the momentum disc system, and it was 2 by 2 plus Ua by V, right. Next, we will define the term thrust loading coefficient in the context of the axial momentum theory. So, this coefficient is basically non-dimensionalizing the thrust generated by the disc with respect to the parameter half rho a into d square, velocity square. So, thrust loading coefficient, which we call as CTL, is basically the thrust generated by half rho AP into v square. So, here v is the reference velocity which we will use to define different parameters of the axial momentum theory. So, for the thrust loading coefficient, we use it to non-dimensionalize the thrust and we will relate it to the ideal efficiency in this particular calculation. So, what is T? T will be rho AP into Vp into UA, right, and in the denominator we have half rho AP V square, right. So, rho AP cancels out. So, what is Vp? Vp is V plus UA by 2 into UA, and we have half V square, right. So, now CTL becomes V plus UA by 2 into UA into 2 by V square. Okay. We can rearrange these terms and write it as UA by V and take the 2 inside the bracket, 2 plus UA by V. Okay. So, this becomes our 4. In this way, what we have done is we have expressed CTL as a non-dimensional velocity equation. So, we have UA and V, where UA is the axial induced velocity and V is the velocity at which the momentum disk is advancing in the fluid. So, given that ratio, we will be able to calculate the thrust loading coefficient. Now, how do we relate this to the ideal efficiency? This is very important in the context of understanding the efficiency of a propulsion system. So, if we expand this equation, CTL becomes UA by V whole square plus 2 UA by V, right. Now, we can write it as a quadratic equation, UA by V whole square plus 2 UA by V minus CTL equal to 0, which is basically of the form AX square plus BX plus C equal to 0, where the variable we can calculate x here, which is UA by V. So, what we do here is we apply the Sridhar-Acharya method and calculate UA by V as minus B, which is 2, plus minus root over of B square minus 4 AC. So, CTL is basically minus C. So, plus 4 CTL by 2A, A is 1 here, 2, right. So, this becomes minus 1 plus minus root over of, so 4 comes outside the root and divided by 2, it is 1, right, 1 plus CTL. Now, when we have a velocity V at which the momentum disk is advancing forward, the induced velocity UA induced by that disk has to be in the same direction as V. So, UA by V is definitely positive. So, we will take only the positive root here. Here UA by V will be root over of 1 plus CTL minus 1, right. So, for all positive values of thrust loading coefficient, you will have UA by V will be positive here. Okay. Now, how do we write eta I? The ideal efficiency eta I was 2 by 2 plus UA by V, right, and from the previous page we see that UA by V is root over 1 plus CTL minus 1. So, we can write it as 2 by 2 plus root over 1 plus CTL minus 1. So, your ideal efficiency becomes 2 by 1 plus root over 1 plus CTL. This is a very important result from the context of axial momentum theory of propellers, which relates the ideal efficiency to the thrust loading coefficient. Now, what does it imply? If you want to get an ideal efficiency of 1, let us say, so what will be the value of the thrust loading? For any value when CTL is greater than 0, let us say, for any positive value of thrust loading coefficient, what will happen to this denominator? 1 plus root over CTL will be greater than 1. So, eta I will be 2 by something which is greater than 2. So, eta I will be less than 1. Okay. So, the only condition where we can get an ideal efficiency of 1 is the case where CTL is 0. Then only from this equation we will have the ideal efficiency equal to 1. Now, what does it imply? If CTL is 0, CTL is defined by thrust by half rho AP V square, right. So, if CTL is 0, then thrust has to be 0. That means the momentum disk is not generating any thrust. So, if it does not generate any thrust, then there is no point in the calculation of efficiency here. Okay. So, for any practical value where the momentum disk is generating a finite value of thrust, we will have the ideal efficiency of this system less than 1. Okay. So, another important thing should be mentioned here is this is a very simplified assumption that in this axial momentum theory the propeller is or the disk is not imparting any rotation to the flow. Now, what happens if we consider a rotation in the flow? If we do that, then the ideal efficiency will be slightly reduced by another fraction which will come from the rotational value. So, here we have the ideal efficiency given by 1 by 1 plus A, if you remember, where A is the ratio of the axial induced velocity at the propeller disk. So, this was basically 1 by 1 plus UA by 2V, which is the ratio UA by 2 divided by V. So, similarly, we can define another ratio if we take care of the rotation, okay, then we will see that it will come to another value 1 minus A dash by 1 plus A. Similarly, where A dash will be the rotational component induced at the propeller plane divided by the rotational speed of the momentum disk, and A here we already know A is UA by 2V. Okay. So, if we consider both the axial and rotational induced velocities, eta I will be reduced further. That means, both the numerator here will be lower and we have a already higher denominator due to the effect of the axial induced velocity. So, this here the numerator is the rotational component and the denominator is due to the axial component of the induced velocity. Okay. So, let us try to look into very simple problems which we can do applying axial momentum theory. Okay. Suppose in this particular problem you are given a propeller of diameter d which produces a thrust T when advancing at a velocity or speed v. Okay. Calculate the different components like power, velocities in slipstream at a section far astern, that means far behind, thrust loading coefficient and ideal efficiency. So, in this given problem, the diameter of the momentum disk is given, which is representing our propeller. So, d is given, which gives us the area of the disk or propeller, we can say is pi d square by 4. Next, the thrust generated is given and the velocity of advance v is given. These are the input parameters. The parameters to be computed, so I write to calculate are power delivered to the propeller, velocity far astern which is v plus the axial induced velocity, the thrust loading coefficient and the ideal efficiency eta I. We start with the given value of thrust and the equation for thrust with respect to the velocity components is given by T is rho AP Vp into UA, where UA is the axial induced velocity and Vp is the velocity at the propeller, which is the velocity of advance or the inlet velocity plus half of the induced velocity far astern, right. So, we can write this as T is rho AP V plus UA by 2 into UA. Now, in this particular equation, thrust is known and on the right hand side all the terms except UA are known. So, when we put the values, we will have a quadratic equation with UA as the unknown and we can solve for UA. So, this gives the value of UA. From this we can now get V plus UA as the velocity far astern because V was already known. So, this solves one part of the problem. Next, eta I is given by 1 by 1 plus A, where A is the fraction given by UA by 2V, which is UA by 2 the axial induced velocity at the propeller plane divided by the advanced velocity V. Now, once we have computed UA, we can calculate this fraction A and this gives us the value of eta I. So, this part is done. Next, we can compute power delivered or power P, however we may write now here, as thrust into velocity divided by eta I. We can use the output power, which is thrust into velocity divided by the efficiency to get the power which is delivered to the propeller. So, this is the same as P which is mentioned here. We know all these terms T, V and eta I. So, P can be calculated and finally, the thrust loading coefficient CTH can be computed as T by half rho area of the disc into V square. In this way, all the terms can be calculated for this problem. Now, the same problem can be given in a slightly different way, where instead of this thrust value, any of the velocity component can be given. For example, either UA or the total velocity far astern may be given. So, we can use the same set of parameters to calculate the value of Vp, right. So, for example, if V plus UA is given, we can calculate Vp by V plus UA by 2. From the value of total V plus UA, we can calculate only UA, and then we can calculate the value of Vp from that, and we can use this value to calculate the thrust, which is unknown if the problem is given in that way. Okay. So, in this way we can use simple momentum theory calculations to do basic powering estimate for a momentum disk where only the axial induced velocity is considered. Another very important aspect of this momentum theory is the relation between the ideal efficiency and the thrust loading coefficient. So, as the thrust loading coefficient CTH increases, the ideal efficiency of the propeller or the momentum disk here will decrease, and only for the condition where this CTH is equal to 0, then the momentum disk will have an efficiency of 1. That means, when the disk is not producing thrust at all, that condition only will lead to an efficiency of 1. So, for any practical condition where a finite thrust is being generated, there is a value of efficiency which will be less than 1. So, if this thrust loading coefficient increases, the ideal efficiency will decrease. On the other hand, if CTH decreases, the ideal efficiency can be increased. Now, this has a simple practical implication. For example, if we have a propeller of higher diameter as compared to another propeller which has a lower diameter, then for the same thrust output, the propeller having the higher diameter can operate at a higher efficiency. So, CTH is basically T by half rho AP into V square. So, if the propeller diameter is higher, then AP will be greater, right. If AP is greater for a propeller of higher diameter, it will lead to a lower value of CTH, that will lower the thrust loading coefficient, and if the thrust loading coefficient is lowered, the efficiency will be higher. That is why it is preferable to have a propeller of higher diameter to obtain a higher efficiency if all the other geometrical aspects are similar. Another problem which is slightly different is like this. You have to calculate the thrust generated by a propeller, okay, where the diameter is given and it absorbs a power P without any forward speed using the axial momentum theory. Okay. So, basically the input power is given, or thrust may also be given, whatever, any one of them can be input, and another one you may be asked to calculate, and we are having a propeller of diameter d, and we would want to calculate at the condition where the forward speed is basically 0. This condition is very special for ships, because later when we discuss propeller in open water condition, we will see that this is called the Bollard pull condition, where the forward speed of the ship is 0 and we have the propeller working in a static condition, and we would want to know the characteristics of the propeller. Okay. So, using axial momentum theory, how can we do that? This is the next calculation example. Now, let us say we have the forward velocity V is approaching 0. We take a limiting condition where V is approaching 0. Now, what is the power delivered is equal to T T into V divided by eta I, right. Now, if we write this eta I as a function of CTL, the thrust loading coefficient, what will it be? It is 2 by 1 plus root over of 1 plus CTL. Okay. So, the delivered power can be calculated as TV into 1 plus root over of 1 plus CTL divided by 2. Now, when the velocity, the forward speed of the propeller, in this case the momentum disk, is 0, what happens to the thrust loading coefficient? CTL is given by T by half rho AP into V square, right. So, when the velocity V is approaching 0, CTL will be extremely high, right, at velocities close to 0. So, in those conditions we can write that as V is approaching 0, 1 plus CTL will approach root over CTL. This is a small trick we need to do to cancel out the velocity component, so that we will be able to relate the thrust to the delivered power. Okay. So, we write the same equation, P delivered will be T V into root over CTL by 2. Okay. Now, if we take square, power delivered square will be T square V square by 4 into CTL. Now, what is CTL? CTL is T by half rho AP V square. See, the V square term can be cancelled out, so that we can get this equation, power delivered square is T square into T is T cube by 4 by 2 is 2 rho AP. AP is the area of the momentum disk here. So, we can use this equation simply to relate the power to the thrust. The delivered power to the thrust can be related using this equation, where we have the forward velocity approaching 0 using the axial momentum theory. Okay. So, in this condition, if the thrust is given, we can calculate the power and vice versa. Okay. So, these are some simple problems we can do using axial momentum theory, and this gives a basic idea of thrust loading and other efficiency calculations that can be easily performed using axial momentum theory, which is a very simplified theory, but it gives some understanding of the efficiency that a propulsion system can have at a given conditions which involve the velocity and basically the thrust that the propeller is producing with respect to the diameter, which is given finally by the thrust loading coefficient. Okay. So, this will be all for today's class. Thank you.